Hello, everyone. My name is Asu Özdaglar. I'm the head of Electrical Engineering Computer Science Department, also the Deputy Dean of the Schwarzman College of Computing. I'm delighted to introduce the session on AI and health and life sciences. It's a very exciting time for this initiative and its intersection with AI. Advances in AI and machine learning are transforming not just every aspect of our lives, but also the fundamentals of academic inquiry. And life and medical sciences are very much at the forefront of this, with the promise of accelerated scientific discovery and personalized treatments in medicine. While the opportunity is clear and present, realizing it is absolutely not trivial. It really requires a two-way exchange between biologists, chemists, chemical engineers, and healthcare professionals on one hand, and those at the forefront of AI and machine learning on the other. And this session aims to contribute to this exchange by highlighting early innovative advances from MIT and how we can make this aspiration a reality. I'm delighted to introduce our four amazing speakers. First is Joey Davis, Associate Professor of Biology. Joey will focus on structural dynamics of multiple molecular machines that are essential for performing critical cellular functions, including synthesis and degradation of proteins. He will present his recent groundbreaking work that develops a novel computational method called cryo-DRGN, leveraging deep learning to analyze data from cryogenic electronic microscopy, which enables to image millions of single molecules rapidly, but also extending this method to determine dynamic structures of protein complexes directly in cells. The second speaker is Caroline Uller, Andrew and Erna Viterbi Professor of Engineering in the Department of Electrical Engineering and Computer Science, also core member of Institute for Data Systems in Society and Broad Institute, and the director of Eric M. Mendy Schmidt Center. Caroline will highlight the big opportunity coming from rapidly growing data sets in biomedical sciences. Of course, there's great promise in understanding programs of life, but also a phenomenal opportunity for AI and ML in creating inspirations and problems for the foundational techniques. Of course, I think the interesting part about her work is she's going to highlight that AI applied to biomedical data will require focusing on causal mechanisms rather than simply correlations and forecasts which is the focus of machine learning in several other domains. And she will actually talk about a roadmap that combines causal inference and machine learning to understand various key questions in cell biology. Our third speaker is Marzieh Ghassemi, Germeshausen Development Professor in MIT Electrical Engineering and Computer Science Department, as well as Institute for Medical Engineering and Science. Marzieh focuses on decision-making in healthcare, and she's going to highlight the importance of evaluating not only model performance, but also the heterogeneous performance of these models, including biases when a model is applied to specific demographic groups. She will investigate whether the AI models currently in use use demographic information as shortcuts and whether biased decisions follow from such shortcuts. But of course, with a positive spin, she will also tell us how to actually debias these outcomes in a way that's sort of calibrated to each distinct input and query. And last but not least, our fourth speaker is Dimitris Bertsimas, the Boeing Leaders for Global Operations Professor of Management and Operations Research at Sloan School, as well as the Vice Provost for Open Learning. Dimitris will conclude the session focusing on precision medicine, providing personalized care. How do we provide personalized care to every patient? Of course, the key here is to understand the variation of treatment effects across patients, meaning how the same treatment will affect different patients differently. Gold standard approach is to use randomized controlled trials, but of course this is very costly and we have tons of observational data, so he's going to present a terrific approach that enables use of observational data by removing unobserved confounding as if they were randomized, thus opening really the road to true personalized medicine. With that, very delighted to invite you.
All right, thank you for that wonderful introduction. So I thought I would start with some slides. Oh, do I need to advance? I wanted to start with sort of a historical perspective. This is a quote from renowned physicist Richard Feynman, and he's sort of describing the interesting biological problems of the day, things like how do cells deal with DNA mutations, how do they perform translation, that is, how do they synthesize proteins, how do things like photosynthesis work? And he says, it's very easy to answer many of these fundamental biological questions. You just look at the thing, right? And I really love this quote. It sort of captures the promise of structural biology. That is, if we could determine structures, we could inspect those structures and use them to infer sort of chemical mechanisms of action to really understand how these machine works. He goes on to say, and lament, unfortunately, the present microscopes, and here he's talking about electron microscopes, they see at a scale that is just a bit too crude. If we could make them more powerful, many of these problems would become easier. Right, and so when we think about what he was describing at the time, we can go and look at a micrograph from around that era. This is a human cell, and it turns out all these little black dots you see are ribosomes. These are the machines that are performing synthesis in the cell. And when you look at them, it's quite obvious, it's very difficult to figure out chemically how are they working. What are the atomic contacts that allow them to perform translation because the microscope is so crude. If we flash forward roughly 20 years, microscopes got better. People were able to infer sort of low resolution structures of ribosomes shown here. These sort of look like clay pottery. We got a general sense of the shape of the molecules, but we really still couldn't see the important details. So the subsequent 40 or so years of research led to huge advancements both in hardware and importantly in software that now allow us to routinely determine structures to high resolution of important biological molecules. And just sort of capstoning Feynman's predictions, I've pulled a couple of recent papers. Here's a complex that was solved determining how this protein complex repairs DNA mutations. Our group and many others have used cryo-electron microscopy to look at the process of translation, understand how these ribosomes work in atomic detail. And there's a recent study sort of showing how one of the photosystems involved in photosynthesis works. Okay, so how does this actually occur? When we perform cryo-electron microscopy, we're going to take a sample of interest, typically highly purified in one state that you're interested in. You'll apply that to an electron microscope grid shown here, and then you're rapidly going to freeze the sample in a thin layer of vitreous ice. That sort of freezes the molecules in whatever conformation they were in, and then we're going to image it. So this grid is about 3 millimeters across. An electron microscope allows us to sort of magnify it up to 100,000-fold. Here I'll show you a 30,000-fold magnification. This is a copper grid. You can see the grid bars sort of separate these into squares, and in these squares there's a thin layer of carbon into which we've etched small holes. Suspended across these holes is this thin layer of vitreous ice, and as you actually look into the holes, you start to resolve, miraculously, individual molecules. Right? So these are single protein molecules directly imaged. Well, how do we use them? We're going to use very typical machine learning tools, such as convolutional neural networks, to isolate the particles of interest. We can extract those from the micrographs, and now we have this sort of ensemble of data, which is tens of thousands to millions of particle images. We're going to use computational approaches to then align all of these images, and once we align them, we can average across them, which reduces the sort of noise, increasing the signal-to-noise ratio, and that allows us to now solve these high-resolution structures. Now, inherent in this notion of averaging is the basic assumption that these molecules are in fact homogeneous. That is, that they're all in the same conformation, they all have the same composition. Anyone that has kids realizes that biology is not in fact static, it is highly dynamic. And so we start to think about, say, drug development, trying to understand what types of pockets we might want to dock a ligand. We can think about kids. So here is a small molecule docking problem. The task is to get the ligand into the binding site. If you look at a static structure, this looks like it should be an easy task. And when you look at the dynamic version of it, there are all sorts of motions, there are all sorts of dynamics that complicate the problem. All right, so what we really want to do is look at the dynamics of this. So how are we going to do that? We began to think about other ways to use this data. So typically you would take your set of images and infer a single structure. We thought instead we could use these images to learn a mapping function. So this mapping function at its base level is going to take these images and learn to map from some position in Cartesian coordinates to some density at that same position. We first showed that one was able to do this, and then later we realized, well, we could modify this function to now take as a second input some condition. Say, where is this molecule in a low-dimensional energy landscape? How do we do this? So this is the work CryoDragon that Asu introduced. This was done in collaboration with Bonnie Berger's group in CSAIL and led by my first student, Ellen Zhang. We built a variational autoencoder. It consists of 2 parts. There's a decoder network that does exactly what I just showed you. It's going to predict the EM density at some position. The way it learns to do that is it generates these model slices, compares them to the input images. If they're the same, the neural networks stay left alone, and if they're different, that's a loss that we can backpropagate to that decoder network. We couple that to an encoder network that will map these particles into a low-dimensional space, and you can sort of think about them as sorting them based on their structures. So the particles get sorted based on what they're similar to, and the decoder can generate structures from those. So how do we use this? Here's an exemplar data set we analyzed. This is a spliceosome, so this is a machine involved in splicing mRNA together. If you look at the static structure, there's regions of it that are highly resolved, shown in blue, and there's other regions that we weren't able to resolve. Those are sort of shown in red. We hypothesized that those are likely in motion, which made it hard to resolve them. When we pass this through CryoDragon, we can now start to see this molecule in motion. You sort of see these dancing motions that help you understand the dynamics of the molecule. So with this in hand, we began to think, well, if we can resolve sort of highly purified molecules like this, perhaps we can push this further and begin to resolve sort of heterogeneous structures out of, say, cell lysates. And we turned to translation as a way to test this. It was well known that ribosomes go through all sorts of conformational and compositional changes as they perform their functions. And about 20 years of work, usually primarily cryo-EM, has resolved sort of key states within this. And we said, well, if these states are important, they should be populated in cells. And if they're populated in cells, then we should be able to just put sort of cell lysates directly onto grids, image them by cryo-EM, sort the particles with something like CryoDragon to resolve each one of these individual states. And so I had a series of really wonderful students and postdocs that worked on the technology to do this. And I'm excited to say this actually works quite well. So we can go through sort of that whole set of translation states that I just mentioned. We can see initiation, sort of building up more and more factors joining to the particle. We can look at translation. We can see tRNAs in different states within the ribosome. We can see these ratcheting motions. And again, the remarkable thing about this is that there's no purification upstream. We're just putting lysates directly onto a grid, and we can sort of fill out this diagram in basically 1 or 2 weeks of work versus these like decades of work. What do we really want to do? We want to understand how these machines work in cells. So how do we go about that? There's a related technology to electron microscopy called electron tomography that allows us to look at structures directly in cells. And so Barrett Powell, a student in my lab, applied some of the similar approaches to CryoDragon and particle picking using convolutional neural networks to try to apply this to tomography. And so what I'm going to show you here is a movie. This is a bacterial cell imaged by tomography. As we slice through that cell, you'll see the sort of membranes on the right side of the image. All of these white sort of speckles, those are ribosomes. We can then segment all of those out to populate the tomogram. We can then extract all of these particles and use TomoDragon to try to find those that are in similar states. And there was a little trick here. We had actually treated the cells with a small molecule named chloramphenicol that binds to the ribosome and inhibits it. And what we were really excited to see is that the resolution of the maps that came back were high enough for actually to see the small molecule drug bound. Oops, jumped ahead there. So this is a small molecule therapeutic bound to its functional target, imaged directly in cells. With that, thank you very much for your time.
I'm super excited to be here and see this establishment of this HEALS collaborative. I think it's really exciting to see all this vibrant community come together here and see all the collaborations that will actually come out of it. So I'm here to talk to you about the unique opportunities that I see at building this two-way street between machine learning, AI, and the biomedical sciences, and why I believe that the life sciences are not only uniquely suited for being one of the greatest beneficiaries of research in AI, but actually also one of the greatest sources of inspiration for foundational developments in AI. So in the life sciences and the biomedical sciences, we've seen a huge data explosion where we're now able to measure the same system in many different modalities. Think of single cells where we can, in one experiment, measure the activity of all genes at the single cell level in 1 million cells at a time. Or all of the imaging data where we can image at subcellular resolution, cellular resolution, tissue scale, organ scale, even whole body scale. And we have all these biobanks where we have access to health data of millions of individuals combined with genetics data of these individuals. So I think the real power here comes from thinking about how to integrate these different views of the same system into some joint space. And so that's really where representation learning, the field of representation learning in AI comes in, where you're trying to identify information about all of these different modalities and combine them into one view that is most informative about the system. And so, that has unique opportunities, right? You can think of multimodal biomarkers that better capture a disease because it can combine all these different views. Or you can think about the opportunities for experimental design, to think about, what is information that is actually captured by different types of measurements, say a cheaper measurement, easier to obtain measurement like a heart ECG, or a much harder to obtain and more expensive measurement like a heart MRI. If you have shared information, right, I could just translate from one to the other. Or what is information that is really only contained in a particular measurement, like a particular protein stain, where you really need to get that measurement in order to get that information out. And maybe you can go even further, right? In the life sciences, generally, we care about getting at the underlying mechanisms, moving from just associations and biomarkers, actually moving on to mechanisms and causality. So maybe multimodality can actually help us there. And so that's the question I want to talk to you about. But before, let's make the case, and I think I probably don't even have to make it here, for why we need mechanisms and causality. So let's take a simple example of fibrosis, where it's still a disease that actually has a huge effect on mortality, and there is still no drug that can revert fibrosis. Now, how do we think about identifying drug targets in this setting? Well, we need to identify, and I should say fibrosis is when the tissue stiffens. And so what you want to identify are genes, proteins that are upstream, so causal of tissue stiffening, and not genes, proteins that are associated with tissue stiffening, but are downstream of it, because these would be very bad drug targets. So it's really critical to understand what is cause and what is effect. For example, for identifying a drug candidate, or protein candidates in this case. However, if we're thinking about the current AI models, they are generally fail miserable in causal tasks. And so here I just want to give you a very, very simple example. So we all know that good warm weather and sunshine is a cause of increased ice cream consumption, right? But if you now go out and you have a gloomy, cold day and you give out a whole lot of free ice cream, well, you're increasing ice cream consumption artificially. That doesn't change the weather because weather is upstream of it. However, if you ask DALL-E, so OpenAI's model for generating images from text, and you should all do this experiment, you ask it to draw an image of an ice cream stand where they're giving out ice cream for free, it always puts good weather in the background, because there is a really strong association between ice cream and good weather. And these models are trained on learning based on associations. They are not trained on trying to identify what are the causal relationships. But that's critical, as I just showed you in the previous example. We need AI models that can actually reason causally. And that's exactly the types of questions that we're working on in my lab. So what does it mean to fully understand the mechanisms in a biological system? So I guess traditionally we would love to get to these pictures, these amazing pictures here by Davidson, for example, of really understanding fully how one gene protein turns on another gene protein, maybe even knowing all the differential equations above it, and really having this full causal picture. Now, the framework for thinking about these regulatory networks causally has been already developed in the 1920s by Sewell Wright. And so that has been, like, the field of causality has been a very, very vibrant field, basically since the 1920s. Now, in causality, actually, until now, basically, there has always been one very important assumption, that we know what the nodes of the network are. So say we assume they are genes, and we have data on the genes, like the activity of all genes, and we would like to infer the regulatory relationships, these causal edges between the genes. But I'd like to argue that in all modern problems in the life sciences, we actually don't even know what the nodes of the network are. Like, let's take the example of cholesterol, for example, where, for a long time we thought that total cholesterol was one causal variable. Well, now we know that's not the case. We actually have two causal variables, LDL, HDL, and they have different causal effects. So we don't actually know. We have to learn what the causal variables are. Similarly, in images, pixels are not causal variables. We have to learn what the causal variables are in any of the imaging data sets that we're collecting. Is it the shape of the cell nucleus? Is it a particular protein and where it is localized? Is it how much of it is and where it is localized? So we have a really more fundamental or really new foundational question in AI where we have to first learn what even the causal variables are, and then from there go on and actually learn the causal networks among them. So over the years, we've taken on this problem and really thought about how, or identified that actually having access to multiple views of the same system, so different measurements or different data modalities on the same system, can really help us understand the underlying latent causal structures. So why is that? Well, so let's think about, what is hard about understanding what are causal relationships is you need to sieve out all kinds of spurious associations. So multimodality can help you do that because we're looking for, or a causal relationship in the system as an intrinsic relationship should be there, whether you're looking at the system from the left, meaning with measurement type 1, or from the right, meaning with measurement type 2, or from the top or from the bottom. So in order to really identify what are these causal relationships or causal features, you should be looking for what is invariant to how you're looking at the system. So trying to understand which information or what information is really shared between different modalities can actually help you get at causality. And so that's really exciting because we have all these different measurements of the same biological system. And so we're always thinking about, well, how can I identify what is actually shared between these different modalities and then actually learn from there. And so I just want to end with one example that we're currently working on in ovarian cancer, where we can, for example, think about, well, what is shared among abundant pathology images that we have access to and newer and much more expensive spatial transcriptomics data, and actually see that there is a lot of shared information. It's actually possible to translate between them pretty well. And you can not only identify what is shared among different modalities, but also what is shared or specific to particular individuals or patients. Now, that's a really important problem. Anyone here who has worked with, say, transcriptomic data or basically any patient data knows that if you look at these data sets, you have such big batch effects that basically every patient always looks like its own data cloud. So it's very hard to see what is actually shared and what is specific to a particular patient. But if you just use these multimodal causal features, you can directly identify, in this case, cancer niches, which are specific to a particular patient, and other cancer niches that are actually shared between different individuals. And identifying these cancer niches, as we know, is really critical for informing therapeutic strategies down the road. So I hope I was able to give you an example of showing why I think it is so important to build this two-way street between AI and the life sciences. I think that, like R.A. Fisher was motivated to develop modern statistics based on applications to agriculture and to breeding. I think here we have the modern life sciences is really going to be a driver for new foundational questions in AI that will really inspire maybe even deeper types of questions that we have seen so far. Certainly that's the case in the field of causality. So thank you very much.
Hi, everyone. I'm Marzia Gassimi, and I'm going to talk to you today about the pulse of ethical AI in health. My lab is the Healthy Machine Learning Lab at MIT, and we focus on evaluating whether there's a need for machine learning in a healthcare setting, developing a robust, private, and fair model if there is, and then potentially deploying that model, understanding how people might use that model for good. what I'd like to start out with, and there will be a quiz later, so remember, you're all gonna, it's final season at MIT. What I'm gonna start out with is the first learning, which is, at this point, maybe based on the presentations you've already seen, you should know that with some caveats, we can predict or generate almost anything if we have the right data and the right models. These are two really fantastic examples of AlphaFold for protein folding and robust prediction of breast cancer risk. And in both of these cases, these were tasks that we weren't very good at and that machine learning really improved, transformed the practice in. That's really exciting. How do we do that? Well, the way that we do this now is by following this pipeline. This is pretty well established. We choose a problem, collect some data, define an outcome, develop an algorithm, and then potentially deploy that model. And if I walk you through this for another prospective application, let's say that I want to do X-ray triage at a hospital, so if you're healthy, I want to send you home. How would I do that? Well, I already picked the problem, and so I would go out and get some data. There's 3 really large publicly available chest X-ray data sets in the US, over 700,000 images. I would train a model. Here I'm training a type of convolutional neural network to predict no finding, which means you're healthy. And then I would look at what the performance of that model was, and here I get an AUC of 0.859. That's really high. Random is 0.5, 1 is perfect, so this is a really good score. And many people don't just stop here, right? They go all the way to FDA approval, and in fact, there's now many hundreds of FDA-approved devices with AI/ML in them that are being deployed across a wide range of clinical subspecialties. This is really exciting. But the second thing to keep in mind is that predicting or generating something well for the average, especially in health, is not good enough. Why? Let's go back and pick on my own work. That performance right there, 0.859, that's really good, but that's one number. What happens when I see the individual performance numbers for different subgroups of patients? When I do that audit, I find that this model underperforms in female patients, young patients, Black patients, and patients on Medicaid insurance. And actually, if you exist in an intersectional identity, if you're a Black or Hispanic female patient, then you do significantly worse than if you were part of a larger aggregated identity. And this is happening in part because medical data is really complex, and you can infer just by looking at somebody's medical note or their medical image what their demographics are, what their biological sex is, what their self-reported race would be, and this is even when you don't give this information to the model. This is also in situations where we've tested doctors and they can't tell based on the medical image or the medical note. And so what this means is that it's actually pretty complex to make a model optimal in a high-dimensional multimodal setting. How hard could this be? Well, let's take a look. Medical imaging is one of the spaces where AI is applied to most frequently in health. And so we looked at a couple of settings where it's frequently applied. This would be for chest X-ray-based diagnosis, for dermatology, and for ophthalmology. And in each of these cases, we're trying to predict an important clinical outcome. And we want to look at how poorly these models do in different subgroups, depending on how we optimize the model. The first thing we found is that the more that a model secretly learns in the layers to encode your demographics, for example, that you are female, the worse it does at predicting the clinical target for that subgroup that is minoritized, in this case, female patients. Put another way, if you're training a model to predict pneumonia and it learns who is male and who is female, it'll predict pneumonia worse for female patients. We then tried to fix this, and we found that if you take data from hospitals in Massachusetts, train the model, and force it to be optimal, meaning all the way on the bottom right-hand part of that plot, very performant on average, and on the bottom, very low fairness gap. Then when you test the model on patients from Massachusetts, it does really well, and so that means modern machine learning strategies can be locally optimal if you deploy them in the settings that they're trained in. But that's not how we train machine learning models right now, even when they're approved by the FDA. We train them in Massachusetts, they get approved, and then we invite the world to use them. And when we take this model and we throw it over to California and ask them to test on their data, we actually find that optimal fairness doesn't transfer. And this has important policy findings for the way that we audit models and evaluate them before they're approved in a local setting, for example, state to state. And this gets even harder when we think not just about deep learning models, but vision language models. Everybody's used a vision language model, I would assume at this point for fun. As Carolyn said, they can give you really interesting results. And they're really good not just at image generation, but they have been used in medicine and clinically adjacent tasks for zero-shot classification and zero-shot retrieval. And they're very good at these tasks. But it's also been pretty well established that they have these problematic human biases in each of these settings. For example, they always tend to generate male doctors. And one of the reasons it's really hard to debias these models is because we have a really simplistic approach to thinking about their mind space. And so here, if I wanted to debias a vision language model, much of the existing work assumes there's a direction for male, there's a direction for female, draw a linear projection and collapse that down. It's fair. But actually, these models are reasonably complex and nonlinear. And so maybe the direction for male and female doctors is very different than the direction for male and female pilots or managers. And so in order to get past this, we actually have to think about doing a more complex nonlinear approach. And so in recent work, what we did is looked at a zero-shot retrieval example where we want to get a picture of a doctor, and we want that to be unbiased between male and female image generation. So when I ask for a doctor, maybe my query gets embedded right there at the star. And if I did a traditional debiasing, I would just project a line, find this middle point between these two spaces, and say, now I'm fair. But you can see here, because it's complex and nonlinear, I'm still closer to all of these pictures of male doctors than female doctors. So I would still just generate a picture of a male doctor. Instead, we propose an approach to bend your debiasing in the direction of the complex nonlinear space. And so don't stop here. Move along this surface until you're at a place where you're equidistant from male and female images, in this case. And this is nice because approaches like this require no fine-tuning of your vision language models, so you can just use a vision language model as it comes to you, and they can be tailored to debias for existing or new queries that come in. The last thing I want you to remember is that good models, even if we debias them, they don't necessarily guarantee that we'll have good outcomes. And so we have a lot of work in the past that's shown that the losses from poor AI can be larger than the gains from good AI. And so we have to be really careful that these models are trained well. We know that doctors are susceptible to poor advice, even when they have expertise. Here we showed radiologists incorrect advice for X-ray images, and they were still fooled by it. And finally, we have work showing that the way that you deliver biased content is more convincing sometimes than the biased content itself. So if you tell somebody to call the police on minority patients, they're much more likely to listen to it than if you say there's a risk of violence at an equal rate for minority patients. So we need to pay careful attention to how we deliver advice from models, not just the advice we give. And so the 4 things you need to keep in mind as you build models along this pipeline are we can predict or generate anything, but doing well on average is not good enough. We need to know that making models optimal is complex. Otherwise, they already would be that way. And good models won't improve outcomes. Instead, we need to move forward with creating actionable insights in human health. Thank you.
Good afternoon. Very glad to be here. What I would like to talk to you about is an area that occupied my thinking for many years. And recently, with 2 of my colleagues, we have made some progress that recently appeared, meaning recently the last month, in Nature Digital Medicine. So what is the story? As many of you know, of course, is that the golden standard in medicine, and many other fields, of course, is to do randomized clinical trials. For more than 100 years, this has been the name of the game. However, RCTs are very expensive and often last very long. Also, while RCTs the conclusions are suitable for the average patient, they may be not appropriate for not the average patient. So there's a need to identify a way to understand what is called heterogeneity of treatment effects, namely more personalization. In contrast, observational data are very widely available and inexpensive. One would argue that the cost of developing a new drug, which currently is of the order of between 1 or 2 billion, is definitely affected by the fact that we have to do RCTs. So what is the challenge on this idea? The presence of confounding bias. Confounding exists, especially in observation data. This is exactly the topic that RCTs try to address. At the same time, RCTs, while strong in identifying whether a treatment works or does not work, they do not define effectively patient subgroups. In other words, they don't typically personalize treatments. There has been some progress of what's called one variable at a time, but I would say quite limited. So what is the purpose of this effort? That we propose and demonstrate, using one clinical example, and later on many, but I only have time for one, a framework to reach clinical conclusions based on observational data. And this is data that we used in collaboration with Memorial Sloan Kettering, that one of my collaborators is from. So in other words, we can now have an approach that can lead to medically valid conclusions based on observational data. The second is that even if we insist to use RCTs, we have a way of personalizing the RCT. In other words, from an RCT, you can actually get personalized information of how treatment should be appropriately personalized. So, in my view, this leads to a way of, which is, in my opinion, something I have tried for a long time, to utilize observational data than RCTs for precision medicine. So, let me tell you, get you a sense of the story. We have some patients that have a particular cancer, a particular type of tumor, what's called GIST, gastrointestinal stromal tumor, that MSK specializes in the observational data set. So these patients have already undergone surgery, and the question is, are we going to give them a particular chemotherapy called imatinib? By and large, today in the world, we offer imatinib as a way of doing it, even though there has been some studies that suggest that there are patients who don't need it and therefore would have benefit by avoiding it. So what is the data that we do have? So for each patient, we have some covariates, what is called mitotic count, the tumor site, and the tumor size, potentially others. And for every one of these patients, these are observational data, we also know whether the treatment was applied, whether imatinib was given or not, and whether or not the patient recurred. So we have the data, the treatment, whether a treatment was given, and whether reoccurrence happened. Of course, there's confounding. What is the notion of confounding here? That treatment was not randomly assigned. So patients who are predicted to have worse outcomes typically tend to get the treatment. So these are not, this is not a randomized trial. So the very act of having the treatment has a higher baseline risk of recurrence, so which is the key difficulty. So, so what we try to do, I will briefly tell you the key idea of how to overcome that. There are two components. I will only have time for the first. But the key here is to take a model, take a machine learning model, take only people who did not receive the treatment and build a classification model of whether they are recurring or not. Notice that this is only based on people who did not get the treatment. Then apply the model for those who did take the treatment. So now for every one of these patients, we have a probability of recurrence for both types of patients. But the patient was only developed for those patients who did not get the treatment. Put them in buckets, okay? So now let's say we put them in 10 buckets between 10%. So within these buckets, we have patients that have similar probability of recurrence. Some of them got the treatment, some of them did not. And then at the same time, we try now to, in each of these buckets, there are, say, 10 of them, we try to make them in each particular bucket so that they are as if were randomized. And how do we achieve that? We try to use optimization. We try to match the characteristics from the data that we have so that patients within every bucket, that includes both treated and untreated, are similar in these characteristics. And we use optimization for that. The specifics are that you would not follow it. I would not have followed if I were you. So key here is that we have a methodology now that in each of these buckets, we are able to match their characteristics. Just to demonstrate the process of confounding, the process of the left, the data on the left shows the survival among those who took the treatment and those who did not get the treatment. And you observe that people who got the treatment are faring worse than the people who did not get because they are healthier. After the matching, after this optimization process, there is still confounding involved, but it has decreased. So there is remaining confounding even after this optimization. So what we do as a second step is, and to demonstrate the effect, is that, so this is the graph on the left shows the percentages of people in each of these buckets who have similar probability of recurrence, but who took the treatment and who did not take the treatment. What the optimization does is on the right, in which we have the same number of people, so we actually delete patients from the observational data, but we don't delete random patients. We delete those patients so that the remaining patients are very similar in their characteristics as well as the probability of recurrence. And then as a final step, we also, because there is, as I mentioned, there is confounding left, we actually train a model where we artificially increase the weight for those patients who received the treatment who did not have recurrence. So the model tries to make better predictions for those patients with a larger weight, since this yields greater improvement. So, so in a way, we clean the data in such a way that we try to subtract confounding from the data. And then as a final step, we apply a machine learning technique called optimal policy trees that was developed in my group to be able to personalize the treatment. And here's the effect for patients from MSK. So you can see that, although you might not see the exact personalization, you observe that when you look at a particular, let's say the mitotic count, if it's above a certain level, you prescribe the treatment. If it's below a certain level, you do other things. So this is definitely a personalization story on the observational data. So how do we know that it has some benefits? We actually took completely new data, unseen data from Poland. And in that particular data, we have observed that while the sensitivity of in the trial data and ours is similar, we were able to actually find 7%, the personalization helped us spare 7% of the patients who would not have benefit from unnecessary treatment. While the result is relatively modest, it shows that there is a benefit by the personalization. This is just on, and this is unseen data, I mean, a completely different study. My final point is how to now personalize trials. So this has been, so the benefit of radiotherapy for patients with what is called truncal sarcomas has been demonstrated in 2 major trials. So MSK, as many other institutions, utilize radiation therapy after surgery. So that's more or less the key therapy today. However, it has been reported that some patients might not benefit from that. So applying a similar story, this is now not observational data, this is randomized data for which we don't know how to personalize. So this data does not have the effect of confounding because it's randomized trials. So we do the optimization and this other part, and we also find a personalized treatment on the randomization data. So this is a general purpose randomized clinical trial that allows personalization. And then we try this approach for data from MSK that are different from the clinical trial. The methodology was trained by the randomized clinical trial data that happened in the early 80s. And then we utilized the data from MSK, observational data over 16, 17 years. We have found that the approach is equally effective in protecting patients, but spares 15% of the patients that they didn't need radiotherapy, and therefore the personalization helped in improving that effect. So of course, since then, this was the original paper. We have tried it in about 10 different studies, from cardiology to oncology to other areas of medicine. And we have found across the board that a benefit by the personalization in studies outside of the data we have. So in summary, what I would like you to remember from this is that the area of trying to find an approach for personalization just on observational data is, in my opinion, a very important aspect in medicine. We hope that the approach would definitely help how to change medical research and also perhaps improve and decrease the cost of developing therapies around the world in a way that provides a road to precision medicine. Thank you.